If you strip away everything else, the universe is mostly empty space and a vast amount of pure hydrogen and helium. But billions of years ago, supergiant stars forced simple elements to fuse together, created new, heavier elements, and exploded them across the universe. Left to drift, these elements are governed by a strict rule of physics. All matter is constantly trying to minimize its combined energy. To reach that lower energy state, these atoms are forced to interact. They bump into each other, stealing or sharing electrons to balance themselves out. That microscopic drive for stability is the engine of chemistry. Early humans harnessed these exact reactions when they discovered fire. We used the energy of that reaction to cook food, to harden clay, and extract metal from ores. By learning how to control the ways matter interacts, we took the scattered debris of dead stars and built modern civilization. This chart organizes all those different types of atoms, the chemical elements. Elements in each column share similar properties, dictated by their distinct structures. Inside an atom is a nucleus of protons and neutrons, but chemistry is dictated by its outer shell of orbiting electrons. Apply heat or pressure, and electrons alter their behavior. Atoms lock into solid crystals, flow as liquids, or are ripped apart into plasma. Tracking how atoms interact at a quantum level is incredibly difficult. Simulating anything more complicated than hydrogen requires advanced computer science and intense mathematical modeling. By mapping out those physical and quantum rules, we can predict exactly when and how a substance will shift its form. When atoms do join together into molecules, they form chemical compounds with entirely new properties. Take highly explosive hydrogen, combine it with combustible oxygen, and get perfectly stable liquid water. But every chemical reaction is bound by strict physical boundaries. The conservation of mass and energy dictates that nothing is ever created or destroyed in a reaction. It only changes form. A common way this transformation happens is through an oxidation-reduction reaction, or redox. This is a direct exchange where electrons are actively stolen from one reactant and given to another. To observe these microscopic transfers, analytical chemists developed an immense array of physical techniques. By separating compounds based on their mass or exact evaporation temperatures, they can measure exactly what a sample is made of. Measuring and controlling these invisible energy transfers gives us the precise instructions needed to manipulate our physical environment. In the field of inorganic chemistry, we manipulate non-living, mostly man-made materials. This allows us to synthesize extreme-strength alloys, industrial catalysts, and high-temperature superconductors. Then there is organic chemistry. This is an entire kingdom of science built almost exclusively around the carbon atom and the complex bonds it can form. Manipulating carbon structures leaves a massive industrial footprint. We use it to synthesize agricultural fertilizers, formulate chemical lubricants, and mass-produce synthetic polymers and plastics. Mastering both of these areas, the inert minerals and the carbon-rich molecules, gives us the tools to produce everything from heavy fuels to precision pharmaceuticals. The most complex application of these physical rules happens inside living organisms. Biochemistry is the study of the chemical processes that drive biological life. That same atomic drive to minimize energy scales up. Simple elements combine to build massive biomolecules: carbohydrates for energy storage, lipids for fats, complex chains of proteins, and the nucleic acids that form your genetic code. Mapping these biological structures directly advanced human medicine. It allowed us to accurately diagnose diseases, map genetics, and successfully perform complex tissue and organ transplants. Even the act of thinking is driven by these same microscopic processes. The brain depends on a constant chemical flow, oxygen being passed through the blood and sugars being metabolized to sustain the neural activity that generates consciousness. Chemistry spans the distance from a single drifting atom to the trillions of reactions occurring inside you right now. It is the physical framework that allows simple matter to assemble into the complexity of human life.